Great. So yeah, just to introduce myself, I'm a PhD student based in London. As we were just chatting before, I'm currently writing up, so I should be finished soon and then moving on to Imperial in a few months. And yeah, roughly speaking, my research is using machine learning methods to study string theory, and in particular, studying Calabi and G2 manifolds in string theory. So yeah, that's one of the things I'm going to be talking to you today about. So using machine learning methods to generate Calabi manifolds. And it sort of work in two parts. So the first half is published, and that's using genetic algorithms to generate polytopes. And now what we're looking at is using another type of another type of machine learning method, reinforcement learning, to generate triangulations of the polytopes as well. And yeah, before I get going, I'll shout out to my wonderful collaborators on this project. So that's Per, Georgi in New Hampshire, Yang, who's my supervisor in London, Ed, who's now at Queen Mary, Vishnu in Wits and Johannesburg, and Andre, who's at the University of Oxford. So a quick outline of the talk. I understand this is more of a maths and machine learning community. So first of all, I'll introduce string theory very quickly and explain why we care about Calabi manifolds in string theory. And then I'll move on to more of the mathematical background and explain how we can construct a Calabi manifold as a hypersurface in a toric variety. And then, then I'll talk about the results in its two parts. So first of all, generating polytopes with genetic algorithms. And then after that, generating triangulations of these polytopes using reinforcement learning. And then hopefully I'll have a couple of minutes at the end just to sort of comment on like the end goal and future directions of the project. And yeah, please do stop me at any point for questions, either unmute or I'll try and remember to look at the chat if there's any questions there. Just what is string theory to start off? So currently in 2024, we have two very good models of physics. We have the standard model of particle physics, which describes the three non-gravitational forces, as well as all of the elementary particles. And then we have the theory of general relativity, which is a theory of gravity. And these two theories work very well in their respective domains, but they don't work very well when you try and fit them together. So, of course, ideally, we'd like a complete theory of physics that incorporates both of these theories. And that's what we refer to as the theory of everything, which is the name of the film that probably many of you have seen. So yeah, string theory is the most promising candidate we have at the moment for a theory of everything. And the main premise of the theory is that rather than everything being made up of zero-dimensional point particles, instead the fundamental object is a single one-dimensional string, and then it's different vibrational modes of the string that will give us the different particle properties we see in the standard model. So one of the big problems that we have in string theory is that it's only self-consistent if we have extra dimensions of space. So rather than the one dimension of time and 3 dimensions of space that we're used to, in string theory, we have 1 dimension of time and 10 dimensions of space. So we have 6 extra spatial dimensions to deal with. And one of the ways we get around this is by saying that the extra 6 dimensions are on some small compact manifold. And this is so small that it's beyond our experimental capabilities, and that's why we don't notice it. So yeah, then our 10-dimensional background manifold becomes a product of the usual 4-dimensional Minkowski space and this small compact 6-dimensional manifold. And then there are some constraints that we put on this manifold that come from physics. And these constraints basically ensure that this manifold is a Calabi manifold. So that's some motivation as to why we care about Calabi and string theory. And yeah, there are many sort of definitions of Calabi that people use. I tend to use this one that's a Ricci flat Kähler manifold with holonomy group SE3. So there are some more problems that we have in string theory. So the first is that, as I said, this manifold has to be Calabi-Yau, but there are many, many possible versions of a Calabi-Yau manifold that it could be. And we don't have a method of choosing the right one. So this is what we call the vacuum degeneracy problem. And we often refer to the landscape of all possible Calabi-Yaus as the string landscape. So that's the first problem. And then the second problem is that even if we know the correct Calabi-Yau manifold, we then need its Ricci flat metric in order to then compute the properties of physics that we would get in that situation. But there are no methods for constructing the analytical Ricci flat metric. So this is the second problem that we have. So machine learning is being used in both of these problems. First of all, it's being used to identify good regions of the string landscape, and it's also being used to approximate Ricci flat metrics on a given Calabi-Yau. So I'm not going to talk to you today about metrics. I'm going to focus more on this first problem. And what I'll show you is that we can use generative machine learning methods to generate good Calabi-Yau manifolds. And so in that way, we hone in on the good regions of the string landscape. So that was my lightning introduction to string theory. Now moving on to Calabi-Yau manifolds. And I want to just explain to you one construction we have for creating these Calabi-Yau manifolds, and that's as a hypersurface in a toric variety. So again, this is an audience which is more maths, so many of you probably know this story, but I'll repeat it anyway. So given a polytope, which is just the convex hull of a set of points in a lattice, we can construct a toric variety. So the first thing we do is we construct the normal fan in the dual lattice to the polytope. And from this normal fan, we take each of the cones and we construct an affine toric variety. And then we sort of glue these affine toric varieties together in order to create the total toric variety. And what Batarev and Borisov discovered in the early 90s was that if the polytope that you start with is one of these so-called reflexive polytopes, and I'll define for you what that is in a minute, then it follows that the resulting toric variety is a Fano variety with at most canonical singularities, and also any generic anti-canonical hypersurface in that toric variety is a Calabi-Yau variety. And the Calabi-Yau variety will inherit any singularities that it encounters in the ambient space. Of course, we want a smooth Calabi-Yau, and so we want to resolve these singularities. And the way we do that is by taking triangulations of the original polytope. And in particular, we take these fine irregular star triangulations, and these will resolve the singularities in the ambient space, and therefore also in the Calabi-Yau hypersurfaces. So what exactly do I mean by fine regular star? Well, fine triangulations just mean that every point is included in the triangulation, and that just means that all of your singularities get resolved. And then a regular triangulation is one you can obtain by basically assigning a height to every point in the polytope, raising the polytope up one higher dimension using these heights, and then taking the convex hull of the higher dimensional polytope and projecting down the lower faces. And this is what gives you your triangulation. And this regularity condition, we want it because it ensures that the resulting toric variety is scalar. And then finally, the star triangulation is it just means that every simplex in the triangulation includes the origin as a vertex. And then this just ensures that we can produce a fan. So yeah, and I'm going to move on now to just focus on the polytopes. But then when I get to the second half of the project, we're going to come back to triangulations. So yeah, as I said, polytope is just the convex hull of a set of points in a lattice. So you can define a polytope by giving the coordinates of its vertices, and this is what we call the vertex matrix representation. But also you can define a polytope as the intersection of lots of half spaces, and each half space is defined by a hyperplane. And so the hyperplane is often given by some lattice point in the dual lattice, and also some real number that basically defines the distance of the hyperplane from the origin. And yeah, this is what we call the hyperplane representation. And you define the dual of a polytope using this equation here in the dual lattice. And a polytope, we say, is a lattice polytope if all of its vertices lie on integer lattice points. So like we see here, we haven't got a vertex, over here somewhere. And also we say a lattice polytope, or a polytope in general, satisfies the IP property if it just contains a single interior point at the origin. So with that, we can define what it means to be a reflexive polytope. So a polytope is said to be reflexive if both the polytope and its dual are lattice, and also the polytope and its dual satisfy the IP property. And there is an equivalent definition of reflexivity, which says that a polytope is reflexive if and only if it satisfies the IP property, and also it contains just a single interior point, satisfies the IP property, and all its hyperplanes are distance 1 from the origin. So that means, yeah, all of these A's are going to be equal to 1. So motivated by Basarov and Borisov's discovery that you can get a Calabi manifold from a reflexive polytope in the late 90s, so a few years later, Porisov and Skarka developed an algorithm to completely classify all reflexive polytopes in any given dimension. So I should say an n-dimensional polytope will give rise to an n-1 complex dimensional Calabi. So in 2 dimensions, these are Calabi 1-folds, and it was already known at that point that there are just 16 of these. And obviously the Calabi 1-folds are the elliptic curves. And then in 3 dimensions, Porisov and Skarka used this algorithm that they constructed to get all of the reflexive polytopes, and they found 4,319, and these are the ones that correspond to K3 surfaces. And then after this, they then moved on to 4 dimensions, and they used their algorithm to classify all reflexive polytopes here. And then they found some 500 million or so. And yeah, these are the ones that correspond to Calabi 3-folds, which obviously are the ones that we're interested in for string theory. So this data set is very largely studied in string theory. And okay, so if we look at this sequence, we have 16 in 2 dimensions, some 4,000 in 3 dimensions, and then already 500 million in 4 dimensions. You can imagine that the total number in 5 dimensions is going to be an extortionate number. So there doesn't exist a complete data set of all the 5D polytopes, but Skarka and Scholler did come up with a partial classification, and in here we have around 185 billion. And yeah, these are Calabi 4-folds, which are interesting for F theory, and F theory is just some sort of extension, I guess, of string theory. So as I said earlier, string theory is in 10 dimensions, and we want to get down to 4 dimensions, so we have 6 extra to deal with, and that's why we use a Calabi 3-fold. And then in F theory, we have 12 dimensions, so we have 8 extra dimensions. So there we compactify on Calabi 4-folds in order to get down to 4 dimensions. Okay, so now moving on to the results. So to generate these polytopes, we decided to use genetic algorithms. And these are super simple to understand because they simply mimic the process of natural selection. So what you do is you start off with a population of individuals. And for us, individuals are polytopes. And in fact, we took our polytopes defined by their vertex matrix, and we converted this vertex matrix into a bit list, so just a list of zeros and ones. The first thing you do is you assign a fitness to every individual in the population. And because for us, we wanted to generate reflexive polytopes, our fitness function gave a score to a polytope based on how close it is to being reflexive. Okay, then once you've ranked your population based on their fitness scores, you then select fit pairs of individuals from the population and you breed them to create a new generation of offspring. And there are many ways to do both the selection criteria and the breeding process, but essentially fit pairs of individuals are selected for breeding based on some probability distribution. Fit of individual is, the more likely it is to be selected. And again, the crossover or breeding process can be done in many ways. Because we were dealing with individuals represented as bit lists, there's a very easy way to do that. And it's just randomly selecting a position in the bit list of two parents, and then you just exchange the bits up until that point to get two new offspring. And then the final thing in the process is to do random mutation. So for us, that just meant randomly selecting a proportion of the bits in the total population and flipping them. So a 0 becomes a 1 or vice versa. And now you're left with a new population, and then you just repeat this process over and over again. And hopefully, if everything goes to plan, and the fitness of your population should increase over time. So as I said, the fitness function for us gave a score to a polytope based on how close it is to being reflexive. So taking the definition of a polytope in its hyperplane representation, we define our fitness function as you see here. For now, let's just ignore this third term and just focus on the first two terms. So IP of delta is 1 if delta satisfies the AP property, 0 otherwise. So if delta is a reflexive polytope, this first term will vanish. And then also in the second term, we have a sum of the distances of the hyperplanes from the origin and 1, and then just averaged by dividing by the total number of hyperplanes. So again, if delta is a reflexive polytope, all of these distances are going to be 1, and so this term will also vanish, which means if delta is a reflexive polytope, we're going to have a 0 fitness score, and then if it's not reflexive in some way, then it's going to have some negative fitness. Okay, now this third term is used when we don't just want to generate reflexive polytopes, but we want to generate reflexive polytopes with a specific number of points, which, as we'll see in a minute, is actually what we did in certain cases. So yeah, just to be clear as well, what I mean by points. So yeah, this polytope has just 4 vertices, but it has the interior point and some points interior to the facets. So these also contribute to the number of points. Okay, so NP of delta is the number of points your polytope, and then NP of 0 is the desired number of points you're after. So again, this term will vanish if we satisfy the condition, and it's going to have some penalty added to it if it has the wrong number of points. And the W's, they're just weights. In fact, W1 and W2, we always set to 1, and then W3, we just set it to 0 when we don't care about the number of points, and 1 otherwise. So just to summarize before I actually show you the results, the method by which we generate our data sets of polytopes. First thing we do is we randomly generate an initial population by basically randomly generating the vertices of some polytopes. And then we evolve this population over several generations by going around that loop I showed you earlier. And then we're left with a list of populations, and then we extract any individual from this list of populations that corresponds to a reflexive polytope, and we save those. And then we repeat that process again with another initial population. And this is repeated essentially until we find all of our reflexive polytopes. So in the lower dimensions, 2, 3, and 4 dimensions, we have a complete classification. So here we just stop the search once we reach the known total. And then for the 5-dimensional case, where we don't have a complete database, we instead will stop our search once no new reflexive polytopes are generated in 1,000 of these runs. So yeah, the total number will plateau. Okay, so obviously it makes sense to start in the easiest case and work our way up. So we started in 2 dimensions where we have 16 unique reflexive polytopes. And yeah, these are just, in the box is just the sort of parameters we set. So the mutation rate, the number of generations, actually these always stay the same for all our investigations. And then we tune the population size and the maximum number of vertices and the vertex coordinate range. This sort of defines our environment for us. So for the 2-dimensional case, the maximum number of vertices of a reflective polytope is 6. And then by setting the vertex coordinate range to be -4 to 4, we define an environment that captures all of the 16, but it's as small as possible. So yeah, this environment contains around 10 to the 11 states. So it's already pretty big. But amazingly, just in a single run of the genetic algorithm, which takes, a matter of a couple of seconds on a standard CPU, we generated all of the 16 unique reflexive polytopes. So moving now to 3 dimensions. Okay, now the maximum number of vertices is 14, and we increase our vertex coordinate range to be -8 to 8. So now our environment is much larger. It's 10 to the 51 states. And yeah, we have some 4,000 unique reflexive polytopes. So you can see that the sparsity of the environment is very low. So we have very few reflexive polytopes in a very, very large environment of general polytopes. But amazingly, even in this difficult situation, the genetic algorithm is still able to generate all of the 4,000 or so unique reflexive polytopes. It did take considerably longer. Now it takes around 100,000 or so runs, but it still managed to find everything. Okay, so now in 4 dimensions, we have the complete classification, but it has around 500 million of these polytopes. So this is a very, very large number. We didn't think it was worth our time to completely regenerate this data set because it would take a long time, and it already exists. So there's not really much point in doing it. We just wanted to prove that we could generate polytopes in 4D. So we just focused on a subset of the total data set, which was those with the lowest numbers of points. So yeah, this is now where we switch on this 3rd term in the fitness. So yeah, the lowest number of points of a 4D reflexive polytope is 6, and then we looked up until 10 points. And these are the number of reflexive polytopes with that number of points as taken from Freudenscharker's data set. And then this is the number of runs it took the genetic algorithm to get the total data set. So yeah, even in 4 dimensions, we're still able to generate complete data sets. So this is exciting, but when we originally set out with this project, we really wanted to test it in 5D because there we only have the partial classification, we have the opportunity of generating new reflexive polytopes and therefore new Calabi fourfolds. So we are very excited to see also in 5 dimensions to be able to generate these. And again, we looked at the smallest number of points as we did in 4 dimensions. And these total numbers now are the number we get to, as I said, once we plateau for 1,000 runs of the genetic algorithm. So obviously it is possible that there are more, and these numbers could technically increase. Say you run the genetic algorithm for another 100,000 runs, you might find another couple more. Also, it could be that we've constrained things too much with this coordinate range, and if you increase this coordinate range, you might find more polytopes. But we still think that these numbers are probably a very good, at least, lower bound on the total number. Okay, so we wanted to compare our generated 5D reflexive polytopes now to the ones that exist in Scarpa and Scholler's database. And I should say that a polytope gives rise to the toric variety. And then, as I said at the beginning, any generic anti-canonical hypersurface in this toric variety is Calabi. So rather, a polytope often gives rise to a whole family of Calabi manifolds. And so it can also happen that you have two different hypersurfaces in two different toric varieties coming from two different polytopes that actually are the same Calabi. So one of the ways to compare Calabi is to look at their topological invariants. So one of the topological invariants you can get just from the polytope information directly is the Hodge numbers. So this is one of the formulas to get the Hodge number of a Calabi fourfold from its polytope information, and there are similar ones for the other Hodge numbers. So yeah, L is the number of points, L star is the number of interior points, and then, so yeah, you're taking some combination of the number of points or interior points of both the polytope, its dual, and faces of the polytope and the dual polytope. So what we did is we took our data set of reflexive polytopes, computed all of the Hodge numbers from these, and then we compared these Hodge numbers to the Hodge numbers in Scarpa and Scholler's database. And we found everything in their data set we had in our data set. And also we had new Hodge data. So this is confirmation that we have, in fact, generated new Calabi fourfolds. So this is like one of the big take-home messages of this project, was that we were able to generate new fourfolds using this genetic algorithm. So that's all very exciting. But actually what I think is even more exciting is what we then decided to do, which was to say, okay, is it now possible to specify the specific Hodge number you want of a Calabi and then input this as like a condition into the fitness function, and then use your genetic algorithm to generate specific types of Calabi manifolds for you. So yeah, we went looking in the literature for an example of where someone was looking for a Calabi manifold of a specific Hodge number. And we found this example. Okay, I know this is more of a maths audience than a physics audience, so it's probably not going to mean anything to the people here, but I'll just state it anyway. The condition is for 11-dimensional supergravity compactified on a fourfold to give you unbroken n=1 supersymmetry. So the condition is that the Euler number is divisible by 24, 224, and 504. And so this is a condition we then put into our fitness function. So obviously now we don't care about the number of points, so that third term we had earlier goes away. And this new extra term basically just penalizes any polytope you generate which isn't divisible by those numbers. Okay, so now with the new fitness function, we then ran our genetic algorithm, and amazingly, just after even just a few runs, the genetic algorithm was able to generate for us some examples of this condition. So this is an example of us using machine learning to generate Calabi manifolds of a certain type. And I think this introduces a whole new approach in studying the string landscape, because the usual procedure so far has really been to generate complete databases by some construction. and then go through these databases and check by hand each one and see if they have the appropriate properties that you're after in like a string phenomenology sort of situation. But this is, in a sense, a wasted effort, because most of the Calabi manifolds you're generating aren't going to be suitable for you. And obviously, in a pure mathematical sense, it's nice to have databases of Calabi, but for string theory, we only care about the ones that are suitable. So this sort of, I think, introduces a more efficient way of studying a landscape, which is specify your constraints from the beginning and then use that in a machine learning sense to generate examples. Okay, so now moving on to the sort of second half of this project, which is what we're working on now. And that is to generate the triangulations of these polytopes. And we are now using reinforcement learning rather than genetic algorithms. We did actually try genetic algorithms. We found that this didn't really work for us, so we switched instead to using RL instead. So just as a summary, reinforcement learning is this algorithm where you have an agent and it interacts with the environment by taking actions and moving from one state to another state, and it receives rewards or penalties based on if that was a good move to take or not. So at each sort of discrete time step, you have a state and a reward, and then you choose an action, and this gives you a new state. And basically, the whole goal is to learn some policy function where it tells you, given this state, what is the best action to take. And there are many different kinds of reinforcement learning. One of the most popular ones, and it's the one that we're using, is what we call Q-learning. So in Q-learning, you are basically trying to learn a Q matrix that assigns a value, what we call a Q value, to every action given some state. And the Q value basically tells you how good that state is. So deep Q learning is where you use a neural network to represent this Q matrix. So the neural network is given some state, and then it will give you a Q value for every possible action in your action space, and then you just take the action that corresponds to the highest Q value. So yeah, the overall training procedure can be sort of summarized as so. You start with a random state, and then you pick an action. So you either pick an action by randomly picking one from the action space, or you pick one by inputting your state to the neural network, getting out the Q values, and then picking the one with the highest value. And this is sort of what we call exploitation versus exploration, which is some big payoff you have in reinforcement learning, which says, is it best to just, go with what I know from previous examples, or do I explore a new part of the environment? So yeah, once you have an action, you get a new state, and then your Q value is computed as basically the difference of the rewards. And then this process is repeated until you reach a terminal state. So for us, we start with some random triangulation, and a terminal state is once we get to one triangulation that is a fine regular star. And okay, so once you've got to a terminal state, you now have this list of state Q value sort of input outputs, and you then use that list to train your neural network, and then we go again. So then we pick a new random state, do this whole procedure again. So you're basically iteratively training your neural network. And then you can do this however many times you like. And obviously, the more you do it, the better your network is going to become. So, okay, how do we encode our triangulation states? Oh, the way we do this is with the nice little trick that I have to admit I learned from a group in Cornell who are actually doing very similar work to this. They're also trying to generate these FRSTs they're using genetic algorithms. And they taught me this trick that if you take Wall's theorem, a consequence of Wall's theorem is that two triangulations of a polytope that have the same two-face restriction, these correspond to two topologically equivalent Calabi-Yau's. So in that sense, you only really need to consider the two-face restrictions to get all of your topologically equivalent Calabi-Yau's. So the way we encode our states is by, first of all, compute all the two faces of your polytope. Then for each two-face, compute all possible fine triangulations. And then you then define a triangulation by just picking one of the two-face triangulations for each of the two faces. And then once you have all of the two-face triangulations, is a way of, combining these to get back to your triangulation of your total polytope. And then an action is then just swapping one of the triangulations of one of the two faces. So yeah, the diagram I drew here, I didn't want to make it look like it's always a bistellar flip. In this case it is, but you could have some much more ugly looking two-face with a triangulation, and an action is just changing it to another triangulation. It doesn't have to be changing it to a triangulation that is close to the one that you started with. Okay, so now we want to define our reward function. So reward is just the difference. It's the fitness of the state you move to minus the fitness of the original state. So as I said, all of the triangulations with two faces, they're all fine already, which means the combined triangulation is going to be fine. So we don't have to check that condition. And then there is a way of always kind of making a triangulation a star triangulation, where you just take the height of the origin and you pull it down, and you can therefore force it to be a star triangulation. So really the only condition we need to check is that the combined triangulation is regular. So that's what our fitness function is going to do, is going to give a score on how regular the triangulation is. So to do that, I want to just introduce something called the secondary cone. So as I said earlier, a regular triangulation is one where you can assign a height to every point in the polytope, you raise it up, take the convex hull, and then you project it down. So you can have two different height vectors, which give you the same triangulation. So for example, you can imagine just taking your height vector and multiplying it by some positive scalar. And then once you do that, the triangulation you get is still going to be the same. So the secondary cone is basically the cone you get. So given a triangulation, all of the heights that get you to that triangulation define this secondary cone. And then it's a result that if your secondary cone is full dimensional, this means your triangulation is a regular triangulation. So with that, we can then determine whether our combined triangulation is regular by computing all of the secondary cones for each of the two-face triangulations, computing the intersection of this cone, all of these cones, and then if this intersection cone is full dimensional, meaning that it has the dimension of the number of points in the polytope, then it is the case that your combined triangulation is regular. So this is how we define our fitness function, is we do this, and then if our intersection cone is full dimensional, we give it a fitness score of 1, and otherwise we give it a 0 fitness score. So that's all of the necessary parts. So this is, again, as I said at the beginning, it's a work in progress. So we've managed to get this algorithm running, and we have it able to generate for us triangulations of the 4D reflexive polytopes, those with low Hodge number H11. So these are the small polytopes. We want to now see if we can do this for the larger polytopes. So the largest reflexive polytope in 4D has Hodge number H491. And this one is very important in the string landscape because it basically dominates the number of triangulations of this polytope. There isn't an exact number known, but it's believed to be so large that most of the Calabi you have in at least the KS database come from this 491 case. So this is studied a lot. Okay, so yeah, we want to see if we can generate triangulations for any polytope, including 491. We want to also do what we did in the polytope case, which is specify properties of the Calabi and seeing if we can add this as extra conditions into the fitness function. So as I said, you can get Hodge numbers from just the polytope information. You don't need the triangulation information, but there are other invariants of the Calabi like the triple intersection numbers, for example, where you do need the triangulation. So yeah, we would like to also combine this with the polytope algorithm and then have them running together. And then you can specify multiple properties of your Calabi and use the combined algorithm to generate examples for you. And then, yeah, just finally comment really on the end goal of all of this. So this is very much just like initial baby steps. But the idea is in a string phenomenology situation, you have some various constraints that you want for your model. And then we would like you to be able to input that into some generative machine learning model. We've used genetic algorithms and reinforcement learning, but this isn't necessarily to say that that is the only way or the best way to do it. There's many other types of generative machine learning methods like diffusion models and GANs and things like this. I think it's definitely going to be interesting to try all of these as well. But just in general, you have constraints from string phenomenology, you input this into some machine learning model, and then you use that model to generate for you string models. So that would in itself be a great thing. What would I think be even nicer is that if this model works very well, then somehow digging into the structure of the machine learning model and doing some sort of feature analysis and seeing maybe if we can get geometric constraints out of the machine learning model that correspond to the string phenomenology constraints. So yeah, it'd be nice to say, you know, I want certain things in my string model. How does this correspond to the geometry of the compactification? And I think, yeah, that's it. So thanks for inviting me again. And yeah, please do ask any questions if you have them, or yeah, check out the paper and the GitHub.